Good afternoon, everyone. Thanks for joining our webinar. My name is Nick Narzinski, and today we're taking a look at manufacturing extensions within Fusion 360. So the CAM technology that you guys have seen in Fusion 360 for the past few years has been technology from HSMWorks. And with the addition of PowerMill, PowerInspect, and FeatureCAM within the Autodesk's wheelhouse, we're starting to see some of that technology brought into Fusion 360 as well. So these are in the form of manufacturing extensions that can be accessed directly in the software through this icon highlighted in red up here, a little wrench looking icon. And you can purchase those with cloud credits, either monthly or yearly. So today we're going to take a look at the steep and shallow strategy in there that's out of PowerMill that has 5-axis machining and collision avoidance. We'll take a look at automatic hole recognition, so using feature recognition to match tools up with certain hole features. And then we'll take a look at the rotary strategy for using simultaneous 4-axis machining. So anything rotary mill, or you can do it on a 5-axis mill as well. And then we'll take a look at in-process and post-machining inspection strategies with the use of probes. All right, let's jump into Fusion 360. So first thing we're going to look at is steep and shallow. So in our manufacturing extensions, once they've been activated, that will be found underneath the 3D milling tab or drop down. So I'm going to go to steep and shallow. So I've got set up here. We've already faced it, roughed it again with a smaller tool, finished the flats, and then we're going to run in this steep and shallow. I've got one calculated here already for the collision avoidance. That one takes a little while to generate. So instead of waiting for it, I've got it pre-generated, but I'll show you how to apply these. So I'm going to go to steep and shallow, and let's find a tool. I'm going to go with tool number 6. And do a selection for my boundary. So I'm going to select it. I'm going to edit that by selecting it again and guiding that toolpath up and around the entire pocket. That looks pretty good right there. So I'm going to hit the plus sign. That's going to project it down as our boundary. So that looks good. Let's go back to an isometric view. Next, we're going to look at the passes tab. So within here, we can specify where we want the 2 different toolpaths to come together. So within steep and shallow, we can have one toolpath for steep passes and another toolpath for shallow passes, and that's just defined by the angle of the surface. So the steep passes are going to be done with step down Z-level passes, very similar to 3D contour. For shallow, on this part, we're going to use scallop. You also have the option to use parallel for that. So the angle we're going to intersect those two at is going to be 45 degrees, and we're going to overlap the 2 tool paths by 100 thousandths. And we're going to start at the top, and let's do a 50 thou step down. That's going to be for that steep 3D contour type tool path on the walls. And then we're going to do the remaining material with a scallop type of tool path. The kernel for this is a little bit different from scallop that you have in your standard 3D scallop toolpath. And I'll show you the difference here in just a second. So scallop, we can have the ability to do step in passes or step over passes, or we can keep that continuous. So let's do continuous. We'll step over at 50 thousandths here also. And I'm going to turn on smooth offsets and remove cusps at junctions. And let's okay that. While that's generating, I'm going to duplicate it and do another one without continuous smooth offsets or remove cusps at junctions, so I can show you the difference here. That looks good. Let's okay that one as well. All right, so this first one's calculated. And so here we can see we get our Z-level step downs, and right about here, we have our 100 thousandths overlap between our scallop passes and the steep passes. So what I really like about this toolpath, they did a really good job at, so this one's continuous, so we don't have a bunch of step overs. It's all one continuous toolpath, so we'll have a better surface finish because we're not leading in and out of the material a bunch of times. But also, we have these corners smooth. They're not, whenever that toolpath has to collapse, it's not coming to a point. It's coming to a nice smooth that keeps the cusps down just a little bit. And anytime we have a large cusp, you get this remove cusped joints, that checkbox. That's what this is doing right here. So that's running the ball mill right back through that area and knocking down those cusps that would have been generated there. So here you can see the difference. I can probably turn them both on and you can see. So without the smoothing, you come to points and you end up with larger cusps, and you wouldn't have that pass down the corner without the remove cusped joints turned on. All right, so that's using just standard 3-axis toolpath, but this toolpath also has the ability to be a multi-axis toolpath. So let me just simulate with that tool. And we're just going to jump straight into steep and shallow. Let the simulation catch up here. So this tool is long enough, we can reach down inside there. Using this tool to finish. So here you can see it starting at the top and working its way down. Doing step down passes on the walls, and then those scallop passes on what it defined with all the surfaces within 45 degrees. Excellent. So then you come back through with maybe a pencil toolpath to finish some of these corner areas that the ball mill was too big enough to fit in. But otherwise, that's a pretty quick and efficient way to get good surface finish on what I consider a mold type of pocket. Another thing I wanted to show you within there is the ability to do multi-axis toolpaths. So there's now the addition of a tool axis tab in this strategy. And here, vertical meaning 3-axis. If I change that to lead and lean, I'll just hover over this here. You can see there on that right image, you have the ability to tilt the tool left, right, forwards, or backwards. You also have from and to point. So from point meaning the tool axis vector is always coming from a specific point and pointing down towards the geometry below that you specified within the geometry tab. And then on the right side image there, we have 2 points. So if you put maybe a point somewhere down below, you can have that tool axis vector always pointing at the point as it works its way around the defined surfaces. You have the same options with from and to curves as well. So same deal, coming from a line down to the part, or going above the part and always pointing that tool vector towards a line. So those are 2 options, or no, from 2 points, so really 5 different multi-axis options there. We also have a collision avoidance, so we can turn this on automatic and just tell it anytime this tool is going to have a collision, go ahead and tilt it to avoid collisions. I can also put a maximum tilt on it. So if I turn that on and put a maximum tilt to my machines, you know, whether it's a BC machine or however it's set up, whatever your limiting axis may be, you can specify that there and tell it to trim toolpaths beyond that. So I already calculated this toolpath with these settings. And that is what this toolpath is doing right here. So let me simulate with that one. And again, I'm going to jump to steep and shallow. All right, so here you can already, I've used a shorter tool. I did not mention that, but this one is using quite a bit shorter tool. So it'll be a little bit more of a rigid setup. So with this 5-axis, if we were running this on 5-axis mill, we could shorten it up, get a little more rigidity out of that tool, run the same toolpath in the same boundary. And here you can see it starting to tilt whenever there would be a collision. So pretty powerful technology that goes into this toolpath. The other thing I really like about it is coming from the new kernel that they put in there. They have really good smoothing options as well. So let me take a look at this one here. If I go back in there on the passes tab and turn on smoothing, we can tell it to fit arcs, or we could do evenly spaced points. So if you have maybe an older control, or you know, you want to limit code because of memory purposes, there's a lot of different reasons you might want to use smoothing. But you can say what you want that maximum spacing of points to be, and it does a very good job. Let's just okay it. And I'll turn on the visibility for points. Give it a second here. There you can see the point distribution on the original one. And let's look at evenly spaced points. With that maximum that I specified, you can see how well it does it, evenly spacing those points out. Obviously, that one would have been more code. So the other option is to do the arc fitting, where you reduce the amount of points to fit arcs over a certain area to replace many G1 points with G2 or G3 arcs. All right, so while that's going, let's move over to the next one we had in our PowerPoint was the Rotary 4-axis toolpath. And there you can see that, fitting arcs in there and reducing the amount of points. So in the Rotary 4-axis toolpath, we've had in the past 2D adaptive, 2D pocket, and 2D contour, having the ability to use wrap toolpaths to do, pocket type of features. But what we've been missing is the ability to do 4-axis simultaneous on, shapes like this that aren't necessarily a pocket, that we want to do a continuous toolpath around it. So we now have a rotary toolpath. So the way this works, let's pick a tool. Where's my ball mill? That one will work. Let's do that one. And so we have a boundary to specify here. So we're working initially from front to back. It's going stock front to stock back. So let's change this to only work on the star shape back here. So we're going to go front, selection, choose any feature on that plane, and do the same thing on the back. Do a selection and select there. I don't want that tool to come all the way up onto the outside edge, so I'm going to offset that by my tool's radius, which is a 1/4 inch. I could have also said tool underscore diameter divided by 2 to get that straight off the tool. And you'll see it. Yeah, it'll populate when I hit OK. On the passes tab here, it's looking for a step over. So we'll do 50 thousandths again. And you have 3 options here. So we can do spiral, where it's again in constant contact, spiraling its way down the part. We can do line, which is going to go parallel to the axis of rotation. And we can do Z step overs, or depending on how your machine's configured, you can do step over passes also around the rotary axis. So you can define that rotary axis on the geometry tab. So this does not have to be, how do I want to word that? The shape does not have to be symmetrical around the axis of rotation. That's another unique feature about this one versus these wrap toolpaths, is you can have that axis really anywhere to rotate this part around to machine these surfaces. So with that, we'll just say okay. And let me turn those points back off. And there's our continuous spiral on the part, so we can simulate that. Let's just turn the stock off. We won't rewatch the simulation of the rest of this part. So there you can see it always pointing that tool at our rotation axis and making its way around the part. Pretty neat toolpath. We also have the ability to set angular limits on this. So let's do it one more time. Actually, let's just duplicate the last one so we keep our same front and back planes. So I'm going to edit that one. And this time I'm going to set an angular limit. So we can use points to tell it where we want to machine this within an angle. So maybe I want to program just one of these from there to there. From here, and then say select endpoint and say from there to there. And I need to change this back. I didn't mean to select that one. So this was right here. And this one was right here. There we go. So now you can see, as I look at it from the side, there's a little shaded region here showing me which area it's going to machine within those 2 points. I can also flip that if I wanted to be outside that region. I'm going to stick inside that region. And for this one, let's do line passes. And when I change it to line, going parallel to the axis of rotation, it changes our step over to be a degree. Let's do a 1 degree step over for this one. And we'll say okay. So there you can see how it works that way. And maybe if that was something unique on that feature, and then you can pattern it around, or however you want to program the rest of them. You can do them each individually, or do a pattern on just that one, circular around that feature. And there's, I think, 6 of them. Yep. And program it that way. So I'm excited about that one. That is Rotary. Let's next jump over to hole recognition. So this is on the drilling drop down, hole recognition. So this launches a dialog box that looks at your entire model based on the setup. So I've already got the milling stuff programmed. So now it's looking at the part and finding all of the hole features that it can on that model. And it's doing an intelligent guess based on those hole geometry, based on the hole geometry of how to machine that. So you still have the ability to come in here and make any modifications that you need to. It's looking at my current sample libraries. I can limit it to a setup plane. So right now I'm in, my setup plane is pointing up. So if I check that box, it's going to really limit the amount of holes that it sees. Or I can uncheck that if you had a multi-axis machine to look at all the holes on any angle. You can also do find by angle, find by diameter if you want to limit some things, thread tolerance size. There's some different options there to limit what it sees as far as the holes go. But then back to the holes, we can go through them one at a time. So here it's going to highlight them in the window, and then you can define over here how you want to machine that hole. So let's say this bored hole in the middle, I'm actually going to mill that out. So I'm going to highlight it and just tell it to ignore that hole. That one looks good. It's drill tap and blind hole, and it found the thread size is 1024 UNC. So you can go through the rest of these one at a time based on the angle that it found them at, and make the changes that you need to based on the hole, if there are any changes. Otherwise, you can say okay. It'll run through. You can see a little status bar in the bottom right here. So it's looking at that, looking at my tool library, matching up all those features and adding the tool paths. And you still have the ability to come back and edit these also after the fact. Turn it on. So there's the milling. get all those pockets on the outside, and then it's going to come through and do the drill operations that we've programmed. So that can save you a lot of time if you guys do a lot of hole drilling. You can also set up templates that it'll find and bring those in as well. Awesome. All right, the next one we are going to look at is probe geometry. So for those of you with a probe on your machine, this is a really, I wish I had this back when I was programming. But we have a probing tab now, and we have the ability to do in-process inspection with this probing geometry. So the way it works, I've got this part programmed, and you can see we come in and do a step down on this hole, and let's just edit that real quick. We have tool wear compensation turned on, so it's posting out the G4142 codes. With wear, still posting out the center of the tool. You just enter your number as a negative in your wear column. So when we run this part, traditionally we then come in and either mic it or do some sort of inspection on it, and if it's out of tolerance, then we would close the machine up and rerun that toolpath after we change the wear. With the in-process probe geometry, we can now program that hole, go to probe geometry. It automatically picked the one that I had in here. I'm just going to select that hole. You can enter in your tolerances for that hole. So let's say this hole had a positional tolerance of 5 thousandths and a size of 5 thousandths. Ooh, not 50. And so that's going to program it to probe the hole. Not too much different there from our old probe WCS, but now we have the ability in here to say when it's out of position from those tolerances that we just specified, what do you want to do? We can tell it to stop with the message after it does that. If it's the wrong size, so out of position meaning XY location, wrong size meaning diameter, and then we also have the ability to update the tool wear. So here I can come in and say select, and that tool path was circular. So I'm looking for the circular tool path. I think it's this one, circular 2. So I can select that and see it sees there that was tool 134. I want 100% error correction. Say okay. So now when let me just post those two out together with just the Haas post. So it's doing the machining up here, and then down here it's doing that probe geometry we just created, and it's going to come in there and update the diameter offset for tool 134. So, or the diameter, the wear. So after it does that, then we can just duplicate this tool path, run it again after that. All right, we get one of them above there. Regenerate that. So now it's going to machine it. It's going to, I should have probably probed both of those. Let's just add that real quick. Oh, approach distance. It was just too small to fit inside that hole like that. So let's shorten this up to, I'll just do it the 100 thousandths for now. So that's going to update the tool wear, and then it's going to rerun the tool path. So maybe you're running 100 of these and you want to check that tool every 10 parts or something like that. I would just come in here and right click and make those two optional. So it'll put your, what's the one? That will maybe, can I post that with optional? I guess I can't put optional for that, but you can have it update and then make this one optional. Turn that back off. Regenerate. So let's just post those 3. I wasn't thinking. You would only want to probe one hole because it's only going to find that wear offset once. You wouldn't need to do them both holes. All right, wasn't thinking there. So let's post that out now. And that was probably the error earlier too. I probably could have left the optional on for the probe as well. And so then you could just turn your block skip off whenever you want to run that every X amount of parts. It's a pretty neat feature. Saves you a lot of time of stopping the machine, getting in there with your measuring equipment, and trying to figure that out. So let me just turn that on and see if it, not protect, but optional. Yeah, all right. That was the error earlier, was having those 2 holes on there. So this should now work. There we go. All right. Pretty neat stuff there. So the last inspection we're going to look at today with inside the manufacturing extensions is the inspect surface. So this allows us to actually post out with a separate post a series of inspection points that we can then run on the machine and have the controller generate a report of its findings on those specific points that we can come back in here and overlay it. So how this works is you go to inspect surface, choose your tool, and then just simply click on different points, and it's going to automatically, depending on what you select, going to make the probe enter normal to that surface and point. So here I can just select a few points all around this part, space them out however you want. And after you okay that, I could then post it out with an inspecting post processor and go run that on the machine, have the machine generate a report, and then I can bring that back into Fusion. So there's a import inspection results back into Fusion, and I've already done it here for these parts. So here's the inspection toolpath that was ran, and then it was inspected back in here, and we have, which one is it? This one. And then we have the inspection results, and it lays it out, telling us green, we hit our tolerance, red, we're out of tolerance. And we can also right click on this and do show results and look at this data point by point, and it highlights it in the window depending on which line you have selected. So you can see what the deviation is. A lot of good information here. You can also generate a report out of this and save that back into Fusion. Here's that report that I have, so I can go view details on web. That's going to open up in Fusion Team, and I can print that out and save it with that parts information, or electronically with the information for that part. So that is using the new inspect surface. So again, to turn those on, it's from the extensions button here. You can also go to your preferences and see some of the other stuff that's being worked on under preview features. There's quite a few other manufacturing extensions stuff in here, like live machine data connection, part alignment. That's used for probing your part before you run it the first time, and that will align your work coordinate system to the parts, how it's laid out. So think of a part that you might be using toe clamps on that you need to, maybe it's a casting, you need to find the angle of a feature or where that hole is located. You can run the part alignment ahead of time and have your work offset and the toolpaths all aligned to that afterwards. And then restrict the 4-axis is a new feature that is currently in flow, so that you can. It's always been a 5-axis tool strategy, but this allows you to lock it down so that you can run flow on your rotary mills, your 4-axis mills. There's one other one that I didn't have in the PowerPoint, and that is trim. So trim, again, coming out of PowerMill. It's on the modify drop down here for trim. This gives us the ability to, from your view window, draw a closed profile around a certain toolpath that'll then trim it to fit. So here is an example of a toolpath where pencil didn't quite give us the results we were looking for on this corner. So what was done here is the pencil was then trimmed away where it didn't, or it looked kind of dirty. It wasn't going to give us the best results we were looking for. Then steep and shallow was added across the same region. And that region was then used to trim and then keep the different areas of that toolpath. So how it works is, let me just highlight this one. I'll go to modify trim, and I'm just going to simply draw a rectangle around that area. And I want to keep outside that boundary and okay it. And then I'm going to do the same thing on steep and shallow. So let me turn this one on now and go to trim. And this time I'm going to draw that same boundary. Make sure I overlap it just a little bit with my previous. Accept that. And this time I want to keep inside that boundary. It's going to rerun its generation, and that's fully parametric. So if you needed to get back to the previous toolpath, I can always right click and delete or discard the modifications. I can also, if it didn't quite give me the results I want, I can highlight it, and at the bottom just simply double click the trim, and I can come back and modify that profile if needed. Pretty powerful stuff. It's not it's only able to be used on most of the 3D toolpaths. But that's probably most of the time when you need it anyways. All right, guys, so that sums up just a high-level overview of all the manufacturing extensions that can be included with Fusion 360 with your cloud credits. Hopefully you guys get a good understanding of what's available there and how to access them. If you guys have any questions, please reach out to us. Here's our contact information, our website, our number, and you can email us at info@teamd3.com. Thanks for joining us. Thanks, guys.